6.3 was on the force of gravity. 6.4 is on friction. We've already got tension in ropes and things like that, and the normal force from surfaces. So as you can kind of see here, what Knight's doing is he's working his way through the catalog, and he's going to help you understand how each of these different forces in the catalog is an interesting example of its own. So for example, we have F drag and F thrust. That'll come after a bit. This is like rocket engines, and this is like air resistance. F spring is not coming for quite a while. That one's extremely interesting, but because it's a little bit complicated, it's not coming for a while. Okay, these we've done. This one we've done. So this chapter here, or this section here on friction, is actually about Fs, Fk, and one more Fr that I haven't even mentioned yet. A typical example of static friction would be a box on a carpet. Here's somebody pushing on the box. Now, what's stopping the box from just accelerating? Well, what's stopping the box from accelerating is that there's some friction on the carpet. So if the person was pushing this way, then until the box breaks loose, which it will if you push hard enough, until the box breaks loose, the carpet is preventing the box from moving. We also, by the way, of course, have here the normal force and the gravitational force. There's four forces on this. So there's four forces on this object. And the one we're interested here in this moment is this one, F sub s. Now there's an amount that you can push on this object and it will break loose. And of course, anything less than that, it won't break loose. So what we can say is that, you know how we have Fs as a vector? We can also talk about the magnitude of Fs. We can say that Fs will be less than or equal to some number. Okay, and now here's the interesting thing. It turns out that that number is best represented by a constant, which we're going to call mu sub s. Mu is a new Greek letter for a lot of you. Mu sub s times, and now here's the thing that's interesting, the normal force. So if I piled something additional and heavy on this box so that the normal force on the bottom of the box increased, and of course the gravitational force on this whole thing going down also increased. So if we see that n is a new larger number, then the amount of static friction that can be generated by the carpet on the object will also be a new larger number. So this is our model. Static friction is a frictional force that can be at most mu sub s, the static coefficient of friction, times the normal force. Now I'm going on to the second case. Let's assume that this person is pushing hard enough on this box that there's now movement. And by definition, we're now into F kinetic. Now F kinetic, rather than obeying a less than or equal to sign, we're going to model it like this. F kinetic, that's the vector, opposes the direction of motion. And Fk, that's the size of the kinetic force, is going to be equal to mu sub k times n. Okay, not less than or equal to, not greater than. It's just equal to mu sub k, which we call the kinetic coefficient of friction, times n. Now I've added an additional equation so that we can do some comparisons. Fs, which is the magnitude of the frictional force when you have no movement, that's always less than or equal to its maximum value, which we're going to call Fs max. Actually, Knight says less than, but it doesn't really matter. F, the static friction, is less than the maximum amount of the static friction. And as we said just a few minutes ago, the maximum amount of the static friction is mu sub s times n. Meanwhile, If you have movement, you've got F kinetic, and its magnitude is mu kn, not less than mu kn or less than or equal to mu kn. The kinetic friction, once you've gotten moving, is mu kn. So now that I've written all the equations, I can say something that's true in the real world, meaning that you can push harder and harder on this box. And for a while it won't break loose, and then once it does break loose, the amount of frictional force that you'll be pushing against will suddenly be reduced. Now I want to turn that claim I just made into a mathematical comparison. I said that the maximum amount of static friction is greater than the kinetic friction. That is, when something breaks loose, the kinetic friction is less than what you had just before it breaks loose. Okay, well, that's just saying that this is greater than this, which is saying that this is greater than this. So we have that mu Sn is greater than mu Kn. Now, n was just the magnitude of the normal force. We can divide that out of both sides. And what we've just learned here from that claim is that the static coefficient of friction is greater than the kinetic coefficient of friction. That just leaves one thing here. He's just given one more name to things. If something's rolling, well, there's tires that are excellent at rolling efficiently, and there's tires that are poor at rolling efficiently. And it partly depends on the size and shape of the contact patch and the material. So what Knight's going to say is that if something's rolling, so let's say I have this whole car rolling this direction, if it's rolling, he's going to say that there's an F rolling, which is in the opposite direction. We're going to call that rolling resistance. The rolling resistance is opposite the movement. And the magnitude of this rolling resistance is going to be a new coefficient, mu sub rolling. That's the coefficient of rolling resistance times, once again, n. So the heavier the car, other things being equal, the larger the amount of rolling resistance. That's the model for all three types of friction that he introduces in 6.4. But we've already got a rich, tremendously rich set of examples in 6.3 and 6.4. So before rushing ahead to 6.5, the right next thing to do is to start studying some of these examples.